So, of course, I'm very glad to be here today, and I'm looking forward to working with you for the next, let's see, about 90 minutes or so. Our topic, as you can see, as you know, already know, is brain matters, and we're going to look into what's going on in our brains when we are learning and teaching languages. So at first I thought it might make sense to answer a couple of preliminary questions, but they are thanks to the great introduction, I can almost skip the part, because the question here is, of course, why am I here today to talk about neuroscience and didactics? How come that I make this connection and that I propose to look at the EFL classroom not only from a didactic perspective but also from a neuroscience perspective? So I think you know enough about the connection. You see here the FO, where I'm chair of English didactics, and I'm still a member of the scientific board at the Transfer Center for Neuroscience and Learning in Ulm. So I think that should do, and I can directly move on to an overview over my talk today. At the beginning, we'll raise the following question: how does the brain learn? Take a look at neurons, activity pathways, plasticity. So this is like basics about learning. Then our second topic will be body movements and learning. In this connection, I'll briefly explain what translational research means, comment on effects, explanations, and of course we'll take a look at the application to the EFL classroom. This will be followed by emotions and learning, positive and negative emotions and their influence on learning processes. Finally, I'll give you a quick 101 in neuromythology, separating fact from fiction. And actually, my talk refers to the book already mentioned, Fremdsprachenunterricht und Neurowissenschaften. So, time to get started. First question: how does the brain learn? First off, let's take a look at the basic structures where learning happens in the brain. And of course, this is the neuron. And the neuron is the smallest functional unit of the brain. And it consists of dendrites, cell body, and an axon. You might have heard that in your biology classes, or if you study biology, you're certainly a pro in this. But actually, I think this is quite important, and I wanted to show you that you constantly carry a model of a neuron with you. If you use your hand and your arm, this is like a model of a neuron. So your fingers are the dendrites, the impulse receiving structures. And here you have the cell body, and this is the axon, the long output fiber. And actually an axon in humans, the axon can be as long as 1 meter or even a bit longer. That's how we are wired. I think that's quite impressive. Anyway, neurons communicate via electrical and chemical impulses, and the synapse is the place where the nerve cells communicate, where several nerve cells communicate. Synapse would be here in my model, yeah, and here are the other nerve cells. Back to the question at hand. How does learning happen? Learning means transmission of signals, strengthening of connections in the brain. So that's where and how learning happens in the neurons, by use of pathways in the brain and via communication between neurons. And as this is an important point, let's elaborate a bit. And by following one impulse on its journey, back to our model, the hand. So I'm trying to use my hand and click anyway. the neurotransmitters dock on the receiving structures here on the dendrites, from where the signal is processed to the cell body as an electrical impulse. The cell body sums up all incoming impulses, from numerous dendrites. And in some cases, the cell body generates a so-called action potential and sends it down the axon. Here you can see it. The impulse, electrical impulse, travels along the axon. And that's how the nerve cell triggers communication with other nerve cells. Are you with me so far? Okay, so you're nodding, that's right. So the question at hand is, when do cell bodies generate action potentials? All the time? No. In very simple terms, an action potential is generated in the cell body when, at a certain moment in time, the incoming impulses from numerous dendrites reach a certain threshold level. Then an action potential is generated. If they do not reach this threshold level, no action potential occurs, which means that no communication happens, no learning happens. If an action potential is generated, it travels down the axon, generated in the cell body, then it travels down the axon, and at some point it reaches the very end of the axon, which means the synapse. And this is the place where the signal has to pass from nerve cell 1 to another nerve cell or to others. And it is facing a challenge down there because usually there's no connection, no direct connection between nerve cells, but there is a gap. So neuron number 1, our neuron here in the model, has to convert the electrical impulse into a chemical one. And this is exactly what you can see in the picture at the synapse. These are so-called neurotransmitters that you can see, so-called vesicles, you could also say little bubbles, that diffuse across the gap between the neurons, and then on the neighboring neuron, this is the presynaptic neuron and this is the postsynaptic neuron, they bind on, so to speak, the docking stations on, again, the dendrites. Next impulse receiving structures. So I would like you to take a moment to explain this journey of an impulse to the person sitting next to you. Just 1 minute, because this is really, really important. This is relevant because this is the micro level of learning. And use your hand, use your arm. Here you go, 1.5 minutes. All right, I think this should do. Thank you very much. Hello. It's great to see you busy explaining the neurons and how they communicate, and I've seen some very active neurons and models of neurons in this room. Thank you very much. That should do. I'd like to add a thought on action potentials. Note that the action potentials here that are generated in a cell body are all of the same strength. So there is no such thing as a strong or weak impulse in your system, no big or small action potentials. And this is a crucial information for us as educators in 2 ways. One, we can see that it matters if and how many impulses reach the brain when we wanted to learn something. 2, it shows us that due to the invariability in strength, the number of action potentials generated in the system is of importance. In other terms, in many cases, learning means repetitive training of our competences. And some people compare the brain to muscle. Actually, the brain can be trained almost as if it were muscle. What we do over and over again, what we think about, can change the structure of our brain. Without action potentials, no change and no strengthening of connections would occur. But luckily, action potentials occur in our brain, and our brain can adapt, which means become extra proficient by repetitive use of corresponding pathways and of corresponding brain structures. So, learning means restructuring of synapses and of dendrites. And this idea of restructuring leads us to the concept of plasticity. Plasticity describes our brain's facility to adapt and to reorganize. And actually the brain is constantly adapting itself. With use, pathways strengthen. And whenever students participate in a mental or physical activity or both combined, that activates a specific pathway of neurons. The pattern that binds the connections is strengthened. And eventually there is growth in our brain, especially at the synapse. There are structures that reinforce and that actually grow. Strengthening means that neurons that fire together connect. Or as Carl Schatz put it, neurons that fire together wire together. We know by now that the opposite holds true too. Neurons out of sync, neurons that do not work, cooperate, so to speak, fail to link. They establish no links. All right? So this is very important for us because it matters a lot what we do, how intensely we focus, how often we train, etc. Because use can lead to abiding change in our brain. And non-use means that networks do not develop or do not fully develop. Without being aware, we all influence the structure of our brain. And as Altenmüller, a colleague who investigates music and the effects of music on our brain, puts it, unser Gehirn ist strukturgewordene Lebensgeschichte. I'd now like to tell you an amazing true story about plasticity. You can read it up in the book, The Brain That Changes Itself. I'll indicate the readings at the end of my talk. This is the story of a woman about my age who felt like she was perpetually falling all the time, every day, all day long. How come? Her vestibular system, her balance system, got damaged due to an infection after some routine surgery. To fight the infection in the body, doctors put her on an antibiotic that, especially in high doses, is known for its undesirable, sometimes even harmful, detrimental side effects. It can, amongst others, literally poison the inner ear, leading to hearing loss, or, as in this case, it can damage the balance system. As a result, patients have an unstoppable falling sensation. And how does this feel? Well, you might be familiar with the comparable sensation when falling asleep or somewhere between sleep and waking. You might sometimes imagine to step into an empty space. Yeah? And then you start up from your sleep and put an end to this disturbing, very discomforting sensation. Fortunately, we can stop the falling sensation, but she couldn't for years. Whenever she walked, She had to compensate by holding onto the wall. She was balancing incessantly, wobbling. That's why you call these people wobblers. And I think you can imagine how desperate she must have been, especially after doctors had told her that there was absolutely no cure. The problem is that actually there is no backup system in our body ready to step in when balance system number 1 is out of order. But luckily, our brain is plastic and able to adapt and reorganize, which in some cases means that it is also able to compensate. A neuroplastician, this is a researcher who investigates brain plasticity, heard about her case and had an amazing idea. He wanted to stimulate the woman's brain so that new pathways would form, pathways that could possibly take over the function of her balance system. He created a device with sensors, linked it to a computer, and then a plate with electrode was placed on the woman's tongue. When she tilted, when she was wobbling because the balance system couldn't kick in, she sensed mild electric shocks on her tongue. Nothing to worry about. It just felt like champagne bubbles. Didn't hurt. Yeah? And these impulses were replacing the impulses usually sent by the balance system. Actually, as it turned out, her brain was decoding the signals, and with the plate on her tongue, she said she experienced moments of peace. And somehow the tingling sensations on her tongue, which normally make their way to the part of our brain which we call sensory cortex, were making their way through a novel pathway to the brain area that processes balance. In simple terms, the tongue took over for the inner ear. Unbelievable, but this is true. And eventually, after many training sessions with the plate on her tongue, the woman was fine, even without the plate on her tongue. So this is an incredible but true story about the plasticity of our brain. And this leads us to the question, if there is an expiration date for plastic changes in our brain. When are people's brains too old or hardwired to adapt, too old to learn? Good news, never ever. For a long time, however, we were led to believe that as we become older, the connections in the brain become fixed and eventually brain cells would be dying. Note that brain cells do die. They can die and do die, for example, from drugs, from abuse of alcohol, toxic substances, brain trauma, maybe even by prolonged lack of sleep. But old age as such is not the major cause of brain cell death. So it is true that as we age, many processes are slowed down, and this holds true also for the brain. But plasticity exists from the cradle to the grave. We are always able to learn. And there is evidence that neural plasticity exists also in older adults, and that's where these little cute rats come into play. If you observe young rats in a sufficiently stimulating surrounding, they usually move a lot, running around, exploring, and so on, whereas older ones, maybe due to arthrosis and pain, show less enthusiasm in running around, which means that as they move less, the brain receives less impulses in motor regions. Knowing that there is a famous formula that describes how the brain works that goes, use it or lose it, what do you think happens in the brain of older rats? Is it too obvious a question? Who gives it a try? Come on. Not all at once. What do you think happens in the brain? There can be growth, but also, as we've heard, yeah, mumbling? Yes, yeah. They lose, deconstruction, so to speak, reduction in the brain. All right, that's exactly it. Now imagine you could put the older rats on a nice cocktail of, let's say, painkillers and some stimulating substances to make them feel young, alive, and kicking again. What would happen? Of course, they would start to reuse their legs, with this use resulting in changes in the brain, until the architecture of the old rats' motor regions would be completely rejuvenated, comparable to the architecture of a young rat. And like my comparison or not, but in this respect, our brains do not differ decisively from rats' brains. Time for an interim conclusion. The brain is plastic, which means it is able to adapt, able to learn even at an older age. Plasticity. The brain learns usage dependently, use it or lose it principle. And usually it takes repetitive activation of the same pathways to influence the brain's architecture and for learning to occur. Many action potentials on the same pathways. So, what could that mean in the EFL classroom? What could that mean for learners, and what could that mean for you as future teachers? What does this tell you? Spontaneous ideas. What would you make out of this? Take 2 seconds to think about it. And yes, here we go.
You can learn language not depending on what age you are, and you learn or you remember those things you can use.
Good point. Yes. Anything else? Yeah, please.
It's better to have it's better to have classes like every day than just once a week. Because you have more information you receive.
Or think about alternative structures that could help you, like use of media at home, homework, and so on, whereas homework is a chapter of its own. Okay. Anything else you'd like to add, please?
Maybe that the Frontalunterricht is really the bad idea, so because only one pupil is triggered pretty much all the time, and all the others are equipped to shut down the system.
Yeah, or it depends on how you organize your input phases. Yeah. Okay. Good. We could say more about this, but let's move on. All right. I like to summarize. It matters what you're doing and what you're learning and how. We'll come back to this later. Plasticity and repetitions and exercises could be useful to trigger repetitive use of pathways and to strengthen pathways in the brain. Use it or lose it principle. All right so far, but what else can we learn from neuroscientific research? And another important question, how can we minimize the danger of misapplication of brain research? How can we know, or how can we be sure to draw the right conclusions from brain research for our classrooms? Let me show you how I'm trying to bridge the gap between research and practice. So, how can this bridging this is the question, how can this bridging from brain research to practice succeed? And this is how I do it. I read a lot of neuroscientific studies, I plan studies, and I participate in interdisciplinary studies, and often with data collected in the lab with the scanner, the brain scanner, EEG, and so on. And how shall I put it? As a former teacher, I often have a hunch that these findings could be interesting and relevant for us as teachers too. But let me make this clear. Our teaching does not happen in the lab, but in the classroom. So I think that there is an immense danger of misinterpretation in the case of direct conclusions. I think the translation of findings from neuroscience to classroom procedures and practices needs a link, and that is what we call translational research. What does it imply? Well, simply before giving advice to teachers, I do additional studies in the classroom, then carefully link my findings to those from neuroscience and take these together as a basis for suggestions and conclusions. Let me illustrate this with an example. A couple of years ago, I came across several studies from neuroscience that investigated the effects of movement-based learning in contrast to learning without movements, such as the so-called NOBJECT study by Kiefer et al. For this study, the researchers invented 64 non-existing objects, NOBJECTs, to make sure nobody knew them. Elimination of prior knowledge. They projected and named the objects. And the elimination of prior knowledge was important as the study participants had to learn the objects' names, they had to learn to match the picture and the name and so on. So the colleagues from Ulm worked within a so-called experimental control design and had an experimental group that learned the objects' names together with corresponding gestures. With NOLO, for example, they might have pretended to hold the object and pull on the grip. And then they repeated in their training session this gesture and said NOLO. Yeah? And they had somehow a link to movement, whereas controls didn't use gestures. And their learning condition resembled a lot what we often do in the classroom, actually, presenting words and pictures, for example. Yeah? What were the results? The experimentals, those who learned it with movement, scored better. They answered correctly and faster than the others. And the EEG recordings, the brain activity recordings, showed higher activity in frontal motor regions of experimentals only. So there was activation in these centers only of those who had learned with movements. As we will see in a bit, the use of movement in learning does lead to higher retention rates, and not only to higher retention rates, but to more stable retention over time. And this is really important for us as teachers. So the use of gestures influences the way in which the brain processes, links, and stores the information, and how successful our brain is in these processes. So we observed a lot of desirable effects in these studies, but even if you might agree that these findings could be important, I think, as mentioned earlier, a direct application to the classroom at this point would have been premature. So this was exactly the point where we said, okay, now it's time to bridge the gap and to look right into the classroom and to see whether this holds true in the real-life classroom setting too. And that's exactly what we did. We carried out several studies in foreign language classrooms, and these are the results of our first study. Participants were teenagers, 14 to 15-year-olds, so learners at the age when hormones are holding brains hostage. And when learning Latin, this was the target language in this first study, seems not to be the top priority in life. And this was our first target group. So they had to learn 18 new lexical items in Latin. The group where it says traditional, they learned the blue line. They learned it without, or learned them without movements, whereas the others used gestures, mime, corresponding gestures, so gestures that make sense. How did it look like? This is what we call scenic learning. That's why it says scenic. Scenic learning describes a procedure where content, for example, new words, is taught together with corresponding gestures, gestures that make sense. And during presentation and especially training sessions, the teacher invites the students to join in the choral repetitions, and then they repeat the lexical items together with the gestures, just mumbling, talking to themselves, over and over again. And they do this link several times. That's how it works. And I think it could be nice for you to get a feeling of how scenic learning works in the classroom. And I thought it would be nice to just do it. So at first, what we need is movements. And I need you to find gestures or a gesture for photographic memory. So I need suggestions, yeah? Okay, photographic. Can we agree on that? Or do you want to suggest a combination, maybe? Memory. Okay, can we agree? Photographic memory. Photographic memory. That's how you would do it in the classroom. Photographic memory. It would be nice for you to join in with me. Let's just do it. Photographic memory. Okay, you would do it several times in the classroom, but we'll come to this after, make it a little bit more complicated for you. Move on to our second item, a guilty conscience. How can you how could you show a guilty conscience? Hiding, maybe? Yeah? A guilty conscience, you somehow hide and you are ashamed. Okay, ashamed of something? You do like a guilty conscience, all right? Let's agree. A guilty conscience. All right, you have, again, let's remember photographic memory, a guilty conscience. Let's take one more. Rebel against parental authority. How could we show this? See, multi-word units work too, not only single words. Yeah? Rebel against parental authority. How would you show it? What's the gesture for rebellion usually? Yes, fist. Okay, so I think that's clear. Rebel against. And how could you show the parental authority? Is there anything? The scolding mom. Yeah. Rebel against, let's do a combination of rebel against parental authority, which is of course a negative image on parental authority, but okay, we can go with that. All right, so I need you to get up. And let's do a little training session, just 1 minute or so. What we are going to do is to repeat all three. So, rebel against parental authority. You do it again. Rebel against parental authority. Rebel against parental authority. Let's take another one. Let's take the guilty conscience. All right. A guilty conscience. Guilty conscience. Rebel against parental authority. A guilty conscience. Guilty conscience. And let's add the photographic memory. Photographic memory. Photographic memory. Rebel against parental authority. Photographic memory. Photographic memory. Guilty conscience. Guilty conscience. Okay, thank you very much. That's basically how you do it in the classroom too. Yeah? You decide. You agree on the gestures, or the teacher brings the gestures to the classroom, and then you do this training session, and they can do it at their rhythm. They can talk, speak up, or just mumble. The important point is that they repeat it several times. All right, let's get back to the graph. As you can see in the graph, in the beginning where it says erster Messzeitpunkt, so test 1, there was no significant difference between the two groups. And after test round 1, the introduction and test round 1, no further training of the words took place in neither group, which means that if you take a look at test round 2 here, you can see something that was amazing to us, because no training after test round 1, but still a rising curve, whereas the traditional group had started to erase from their memory. So this was like kind of miracle learning without training, or what? And then, as you can see, that the results remained stable on a very high level for the movement group. Approximately 16 words out of 18 were remembered over weeks and months, whereas the group without movement could only remember around 3. And that makes a difference. Of course, we did this, we replicated the study with in English classes, French and Latin again, with so-called consistent results. This phenomenon occurred over and over again. We had the same results. Which leads us to the question, how is it possible that the movement group scored better? So a first attempt to explain this phenomenon leads us to brain structure called hippocampus. And the hippocampus, here it is part of the limbic system. And the limbic system is where emotions are processed. Limbic system consists of several brain structures that constantly influence our thinking and decision making. So there is actually no such thing as a completely rational decision making, even if you believe so. Together with the amygdala, this is the little black bubble on the left of the hippocampus. The hippocampus acts as a bottleneck structure to our brain. It's the amygdala's function to assess the harmfulness of inputs and situations, whereas the hippocampus acts as our novelty detector. Our detector for everything in our surrounding that is unusual, extraordinary, remarkable, touching, and so on. So if teachers present content coupled to movement, it has, in most classrooms, a novelty effect, or at least an effect of change to long sedentary time. As a consequence, the hippocampus gets activated, and the hippocampus plays a very important role in learning. Many inputs are processed in the hippocampus, and during a phase called consolidation, the entries get sorted out, and if worth getting stored permanently, they have to get transferred to a larger brain section, namely the neocortex, as the hippocampus is fast but relatively small, approximately the size of your pinky finger. That's the hippocampus. So in summary, we can say it is desirable to, figuratively speaking, get the hippocampus's attention, for example, by the use of movements. Let's take a moment to summarize what we have learned about body movements and the enhancing effects of body movements on learning. We were able to show positive effects on retention when students learn content together with corresponding movements. Connecting several stimuli leads to more effective processing and enhances the encoding process. Or, as Eric Kandel, a very famous neuroscientist, put it, the better something is encoded in memory, the easier it is to recall. End of quote. We observed weaker effects if students did not perform the movements on their own, if they only observed the teacher. But if they do the movements and repeat movements and content together, a couple of repetitions suffice. Afterwards, our brain remembers the movements without us performing it anymore. So your brain remembers the movements, without you performing them anymore, and motor centers keep being activated. We observed strongest effects on long-term retention, which means stable memory over time. So keep moving in your EFL classroom. It's simple and quite effective. The question at hand is, how can we explain these effects? Why do movement groups forget less than the others? There must be something going on in the brain that students are not aware of, triggered by the movements. But what exactly is it? So first bit of my explanation would be multisensory learning. What data shows us is at least partly due to multisensory learning, or as we call it in psychology, multimodal encoding. Note that learning consists of two complementary parts or processes. First, the encoding process, which means the confrontation with new knowledge and skills, the intake phase, and second, the aforementioned consolidation phase, the sorting out, the transferring from limited brain structures to larger brain structures. I'll come back to this later. Multisensory learning influences the way intake is processed in the brain as it activates additional brain centers and leads to the creation of more links than monosensory learning. Second, student activation. So there is evidence for the claim that the effects only show when students do the movements on their own. Student activation is a key factor in this. 3, there's reason to believe that the retention effects observed are due to unconscious repetitions. Let me explain this. We believe that when children play or do spare time activities that involve body movements, they unconsciously reactivate pathways in their brains whenever movements are alike, close to those used in the classroom. With these movements triggering repetition of content without the students being aware of this reviewing process. 4, as already mentioned before, consolidation phases are essential for learning to occur. Input alone does not guarantee learning and progression. As you can see in the picture, there's a close connection between consolidation and sleep. Sleep offers us ideal conditions for consolidation, as the input from the surroundings is limited, with us closing our eyes, for example, blocking out visual impulses and so on. While we are sleeping, the brain is highly active and busy as it decides what to keep and what to erase and how to link new entries. So sleep is important. We are also beginning to see what dedicated or devoted educators have always known, the use of movement makes it easier for learners to understand meaning. Thanks to body movements, language becomes palpable and comes alive. Learning with gesture, mime, and body movements makes it easier for us to form links and connotations. Plus, movements enhance the formation of corresponding pictures in the mind. For example, with the scolding mother, I instantly had a picture in my mind, okay? So that's very important for learning to succeed. Movement-based learning or movement-based teaching is teaching with the brain in mind. What is more, movements often lead to an enhancement of the learning experience, bringing together cognition and emotions. And this leads us to the next topic, the influence of emotions on learning. In the picture, you can see the biochemical ingredients of love, any kind of love. Oxytocin, vasopressin, and dopamine. And dopamine, the third major ingredient of love, is the neurotransmitter that is associated with the brain's pleasure, motivation, and reward system. Dopamine also triggers pleasurable learning experiences. I'd like to stress that emotions have a strong influence on what we learn, how we learn, how stimuli are processed and stored in the brain, and on whether we remember or forget. Thanks to neuroimaging, like fMRI, functional magnetic resonance imaging, and this is an fMRI machine, we have the possibility to scan the brain and shed some light on what is going on in the black box. fMRI images, as these, show us the activation patterns in the brain while subjects perform tasks. And that's what negative and positive emotions look like in your brains. It does not take an expert to tell that it is not the same. Speaking in terms of brain activation, we can clearly see two different activation patterns. And it is due to this difference in activation that we learn better, feeling at ease, relaxed, happy, than under pressure or when we are afraid. In conclusion, we can say that positive emotions clearly outperform negative ones when it comes to learning. Negative emotions make it harder for our brain to learn. But still, as you can see in our graph or in the slide, unless there is totally debilitating fear in our system, our brain keeps on learning. I'm sure you know about the desirable effects of positive emotions on learning. Note that the brain, as the organ that is responsible for learning, is always learning, even under pressure. So there's no black or white picture here. The important message for us is that we learn better and differently with positive emotions than with negative ones. And why is this so? How is it possible that negative emotions may have a detrimental effect on learning after all? In a nutshell, it is because of the amygdala, the second part of the limbic system mentioned earlier. So the amygdala causes, or the activation of the amygdala causes intense emotions in us, especially fear or repulsion and so on. But it is a common misunderstanding to reduce the amygdala's function to negative emotions. Above all, the amygdala is our alarm system in the body, the checkpoint of all incoming stimuli. And when we are under a lot of pressure, feel stressed or afraid, the amygdala is on and it is communicating with other brain structures, other brain regions, thus blocking certain learning mechanisms. As a result, we are not able to be creative, for example. What is more, we know by now that knowledge and competences are stored together with traces of the emotions that we attribute to the content. It comes as no surprise that our brain prefers positively charged entries to negatively charged ones. So whenever you retrieve something from your memory, you automatically re-trigger the emotions or traces of these emotions. And our brain strategically avoids the reactivation of entries that would put us through the pain of re-experiencing stress, anger, grief, or whatever. Hence, the brain does not link the negatively connotated entries or avoids linking them to already existing entries, making it easier for us to forget. As an interim conclusion, I'd like to confirm that positive emotions are desirable. Our brain is receptive and we are willing to link and store inputs. So positive emotions contribute to optimal conditions for learning and maximum receptiveness. In a positive state of mind, we experience learning as rewarding. Then dopamine is released in our brain, the reward substance. Upon this, let us take a quick look at our overview. We've talked about our basic learning structures in the brain, discovered the encouraging results of studies on body movement and learning. We have taken a look at the influence of emotions on learning, which means that it is now time to move on to our 101 in neuromethodology, separating facts from fiction. Start with a quick definition of what neuromethodology means. According to the OECD, neuromyths are defined as a misconception generated by misunderstanding, a misreading, or a misquoting of facts scientifically established by brain research to make a case for use of brain research in education and other contexts. Let this sink in for a couple of seconds. All right, key terms here would be misunderstanding, misreading, misquoting. Now, I'm really curious to learn about your knowledge in neuromethodology. Do you know any myths connected to the brain? Like, for example, the one according to which we have to drink a lot of water so that the brain floats, which is not true. Of course, you have to drink a lot of water. Anything you've heard and said, I don't know, I'm not sure, sounds great.
Listening to Beethoven makes you smart.
Wonderful. We come back to this if we have enough time. Good point. Very, very popular neuromyth. Yes. Another thing, maybe connected to the hemispheres, the two halves of our brain and learning languages. Have you heard anything about that? Very lucky you.
The left hemisphere is dealing mostly with the language and the right one with mathematics and the other counting is not so.
Yes, which is partly true, and then again, it's not true. Yeah?
How about most people only use 5% of their brains every day?
Great myth. Yeah, total, yes. Yes. That's one of the biggest myths, yeah. That's totally wrong. Why would you carry like 95% of brain substance with you? Yeah? That's against the laws of how our brain functions. Yeah? Maximum effectiveness is the basic, or is the basic functional principle of our brain. Yeah. Anything else? So something to do with language is only, the seat of language is only the left hemisphere, which is not totally true, which would mean that maybe in the EFL classroom the right hemisphere is off, yeah? Not true, and so on. So let's take a look at, and this is my last point, I'd like to shed some light on 3 selected myths. Number 1. I'm a sleep learner. Well, not me, but some people claim to be sleep learners. So, sleep learning is based on the assumption that sleep offers ideal conditions to convey information to sleeping persons on a subconscious level, usually by playing recordings. Let me quote from an ad. It's the most incredible learning aid for years, takes the stress and effort out of learning. Sleep learning taps into the brain subconscious while you sleep, allowing anyone to learn any subject with less effort. Effortless learning? That's what many students dream of, isn't it? Well, but honestly, sleep learning sounds quite science fiction to me. And actually, if you believe in sleep learning, I'm afraid I have to spoil the party. Sleep learning is, in fact, an excellent example of brain science being misapplied. Sleep is an important mode for learning, but as we all know by now, we have to differentiate between the encoding phase, and these demand wakefulness, concentration, receptiveness, focus and attention. And the second, the complementary phase, consolidation. Während sich die Annahme, im Schlaf könnten aktive Aufbauprozesse stattfinden, also beispielsweise über Kopfhörer Wörter gelernt werden, als irrig, wenn auch marktstrategisch reizvoll erwiesen hat, wird im Schlaf intensiv nachbereitet. Letztlich also doch gelernt, aber eben konsolidierend. All day long, our brain is constantly busy. 10 million stimuli reach our brain every single second. Being literally bombarded with information, our brain has to radically filter out in order to make sure that important stimuli can be processed. We estimate that 20 impulses out of the 10 million mentioned earlier make it through the filter. Still, the processing of 20 impulses per second is a tremendous job. In between the active processing and encoding phases, our brain lapses into shorter consolidation phases, consolidation modes, also during the day. So if you, as a future teacher, observe students who are daydreaming, it might be a visible sign of consolidation, or else of boredom. Anyhow, I'd like to stress that sleep is particularly precious and important for consolidation processes as a major contributor to learning. Don't put your consolidation processes at risk. Have many good night's sleep. And talking about sleep, myth number 2 is also linked to the sleep mode. Yeah, this is a classic. This is a classic in the domain of myths on effortless learning. I sleep with a book under my pillow, so spend your day hanging out, going shopping, gaming or whatnot, but at nightfall, make sure to put your book under the pillow so that the content can magically be transferred to your mental store while you're asleep. Again, spoiler alert, as you all know, maybe from personal experience, doesn't work. All you can count on with this method is a stiff neck or a bad hair day or both combined. But there is one thing that you should know about sleep and the aforementioned consolidation processes. If right before sleeping you reaffirm what you have consciously learned during the day, or if you leave a small portion of what you have to memorize, let's say up to 7 new words, for example, and give them your full attention before going to bed, having a good night's sleep immediately after this brief learning session, chances are that you have mastered this knowledge in the morning. How come? There's a simple explanation. The freshest imprint in your short-term memory when falling asleep, which means when changing gears from encoding to consolidation, is this brief learning session. And there's every likelihood for this content to being successfully consolidated, as it is the most recent memory that is processed. Well, if there are no competing memories. So really focus and then turn off the light and try to fall asleep. We know, based on empirical knowledge, that learning is most efficient when you rest after learning. And even a short nap can be beneficial for memory and have positive effects and maximize the learning outcome. Are there any questions so far? Or anything you'd like to add? Maybe share something? No? All right. Recent studies indicate that we can trigger the strengthening of previously acquired knowledge during sleep by the use of odor and scent recognition. This is not a myth. This is true. How does it work? Well, if during learning you get exposed to scent, like let's say rose petals, for example, and you have someone at hand to considerately watch your sleep and re-expose you to the rose petals scent during certain sleep phases, inefficient during REM sleep, by the way, then thanks to the odor recognition, your brain reactivates the corresponding knowledge and you will have mastered it in the morning. There are real solid studies on that. From what we currently know about odor-dependent reactivation, all it takes is a conditioning phase, which means an encoding phase being exposed to the scent, and of course an adoring mother or a dear friend who's willing to deprive himself of his sleep in order to watch over your sleep. And to expose you to the scent at the right moment. Well, how doable is this? I don't know. And let's move on to our last myth. And I'll come back to your suggestion with number 3 here. Not Beethoven, but Mozart. Yeah, music makes me clever. The Mozart effect. It is true that music is part of our life and can have positive emotional effects on us, no doubt. Music can be stimulating, energizing, soothing, etc. Music plays an important role in routines and communication between caretakers and babies, for example. as well as in social and religious rituals. Of course, music can also be used in the EFL classroom, for example, as a ritual, a refreshing phase, a stimulus for body movements, or also a boundary or a transition marker between activities, to name just a few. But does listening to music make us smarter? Back in the 1990s, there was a report in which a psychologist and her team from California claimed that people actually perform better, at least on certain tasks, such as recognition patterns or folding paper, if that's what matters for you, after listening to Mozart for 10 minutes. Preferably the sonata, Köchel catalog 448 in D major, if you want to try this out. So soon after this report, there was a surge of interest and fascination, and the Mozart effect quickly became a marketing tool. And here are some headlines from the 19s, where you can see it. Yeah. Clever, thanks to Mozart, and so on. Years later, additional studies started to cast doubt on these findings, and especially on their false interpretation or over-interpretation, like higher EQ after exposition to Mozart sonata. In summary, let me quote from Jenke's book, Macht Musik schlau. Der vielbesprochene Mozart-Effekt konnte wissenschaftlich nicht bestätigt werden. Es kann jedoch nicht ausgeschlossen werden, dass sich bei einigen Versuchspersonen nach dem Hören von Mozart-Musik oder anderer Musik ein spezifisches Hirnaktivierungsmuster einstellt, das eine optimale Grundlage für kognitive Aufgaben bildet. If there is such a thing as a positive side effect, or it might also be a residual effect of music, or that makes people who have listened to music perform better in certain tasks, note that evidence suggests that the positive effects can not only be triggered by music, Mozart, or any other. The important point is that the person likes the music. It's got to be your favorite music, and that the music has a stimulating effect, as in contrast to lulling to sleep. That doesn't work. The same effect, however, might be induced by other non-musical stimuli, maybe by playing with your pet, or there is already existing evidence by listening to the audio recording of a powerfully written short story. Same effect. Then positive effects can be observed in the performance of spatial tasks. Researchers have also found proof for minor positive effects on verbal intelligence, but all positive effects rapidly vanish again. So far, there is no evidence for long-term or spillover effects of exposure to music to our general intelligence. And that's basically it for today. That was my last myth that I wanted to share with you. Now I'd like to show you the main readings. Indicated in blue here is the main source, my book on Fremdsprachenunterricht und Neurowissenschaften, then a couple of other articles and books, some more. And this is the moment to thank you for your attention and your participation. It's been a pleasure, and I hope you all have a wonderful day and rest of the week. Thank you.